Hello, and welcome to today's reading of Biological Psychology 13th edition, carrying on Chapter 1.2, The Myelin Sheath and Saltatory Conduction. In the thinnest axons, action potential travels at a velocity less than 1 meter per second. Increasing the diameter brings the conduction velocity up to about 10 meters per second. At that speed, an impulse along the axon between a giraffe's spinal cord and its foot takes about half a second. To increase the speed still more, vertebrate axons evolved a special mechanism, sheaths of myelin, an insulating material composed of fats and proteins. Consider the following analogy. Suppose your job is to take written messages over a long distance without using any mechanical device. Taking each message and running with it would be reliable but slow, like the propagation of an action potential along an unmyelinated axon. If you tied each message to a ball and threw it, you could increase the speed, but your throws would not travel far enough. The best solution would be to station people at moderate distances along the route and throw the message-bearing ball from person to person until it reaches its destination. The same principle applies to myelinated axons, those covered with a myelin sheath. Myelinated axons, found only in vertebrates, are covered with layers of fats and proteins. The myelin sheath is interrupted periodically by short sections of the axon called the nodes of Ranvier, each one about 1 micrometer wide. In myelinated axons, the action potential starts at the first node of Ranvier. Suppose an action potential occurs at the first myelin segment. The action potential cannot regenerate along the membrane between the nodes because the sodium channels are virtually absent between the nodes. After an action potential occurs at a node, sodium ions enter the axon and diffuse, pushing the chain of positive charge along the axon to the next node, where they regenerate the action potential. This flow of charge moves considerably faster than the regeneration of an action potential at each point along the axon. The jumping of action potentials from node to node is referred to as saltatory conduction, from the Latin word saltere, meaning to jump. The same root word shows up in the word somersault. In addition to providing rapid conduction of impulses, saltatory conduction conserves energy. Instead of admitting sodium ions at every point along the axon and then having to pump them out via the sodium-potassium pump, a myelinated axon admits sodium only at its nodes. In multiple sclerosis, the immune system attacks the myelin sheaths. An axon that never had a myelin sheath conducts impulses slowly but steadily, but an axon that has lost its myelin is not the same, because it lacks the sodium channels where the myelin used to be. Consequently, most action potentials die out between one node and the next. People with multiple sclerosis suffer a variety of impairments, ranging from visual impairments to poor muscle coordination. The refractory period. Consider the action potential while it is returning from its peak. At that point, the electrical potential across the membrane is still above the threshold. Why doesn't the cell produce another action potential during this period? If it did, of course, it would endlessly repeat one action potential after another. Remember, at the peak of the action potential, the sodium gate snaps shut. As a result, the cell is in a refractory period, during which it resists the production of further action potentials. In the first part of this period, the absolute refractory period, the membrane cannot produce another action potential regardless of stimulation. During the second part, the relative refractory period, a stronger than usual stimulus is necessary to initiate an action potential. The refractory period depends on two facts. The sodium channels are closed, and the potassium is flowing out of the cell at a faster than usual rate. In most of the neurons that researchers have tested, the absolute refractory period is about 1 millisecond, and the relative refractory period is another 2 to 4 milliseconds. A toilet is similar. During a short time right after you flush the toilet, you cannot make it flush again, an absolute refractory period. Then follows a period where it's possible but difficult to flush it again, a relative refractory period, before it returns to normal. Please look at your textbook. Let's re-examine figure 1.17 for a moment. As the action potential travels down the axon, what prevents the electrical charge from flowing in the direction opposite that in which the action potential is travelling? Nothing. In fact, the electrical charge does flow in both directions. Then what prevents an action potential near the centre of an axon from re-invading the areas that it's just passed? The answer is that in the areas it has just passed, they are still in their refractory period. Local neurons. Axons produce action potentials. However, many small neurons have no axon. Neurons without an axon exchange information with only their closest neighbours. We therefore call them local neurons. Because they do not have an axon, they do not follow the all or none law. When a local neuron receives information from other neurons, it has a graded potential, a membrane potential that varies in magnitude in proportion to the intensity of the stimulus. The change in the membrane potential is conducted to adjacent areas of the cell in all directions, gradually decaying as it travels. Those various areas of the cell connect with other neurons, which they excite or inhibit. Local neurons are difficult to study because it's almost impossible to insert an electrode into a tiny cell without damaging it. Most of our knowledge, therefore, has come from large neurons, and that bias in our research methods may have led to a misconception. Many years ago, all that neuroscientists knew about local neurons is that they were small. Given their focus on larger neurons, many scientists assumed that smaller neurons were immature. As one textbook author put it, many of these neurons are small and apparently underdeveloped, as if they constituted a reserve stock, not yet utilized in the individual's cerebral activity. Woodworth, 1934, page 194. In other words, the small cells would only contribute to behavior if they grew. Perhaps it's this misunderstanding that was the origin of the widespread, nonsensical belief that they say we only use 10% of our brain. Who are they, incidentally? Other origins have also been suggested for this belief. No one is sure where it originated, but people have been quoting it to one another since the early 1900s. This belief has been remarkably persistent given its total lack of justification. What does it mean? Does it mean that you could lose 90% of your brain and still behave normally? Good luck with that one. Perhaps it means that only 10% of your neurons are active at any given moment. Depending on how we define given moment, 10% could either be an overestimate or an underestimate, but in any case, irrelevant. If you could contract all your muscles at one time, you would not be able to be a great athlete. You would just have spasms. If you could activate all your neurons at one time, you would not have brilliant thoughts. You would be having an epileptic seizure. Any meaningful thought or activity requires activating some neurons and inhibiting others, and the inhibition is just as important as the excitation. You use all of your brain, regardless of whether you are using it well. Module 1.2. In closing. As you have been reading about action potentials and sodium gates and so forth, it probably seems that it is remote from most issues in psychology. Well, you are right. But all these physiological mechanisms are the building blocks that we need to understand before delving into synapses, the connections between neurons. Synapses are the decision makers of your brain, but the input into these decision makers is the on or off messages transmitting down axons. All the glories of human experience originate from the simple chemical processes we have seen in this chapter. Summary. The action potential transmits information without loss of intensity over distance. The cost is a delay between the stimulus and its arrival in the brain. The inside of a resting neuron has a negative charge with respect to the outside, mainly because of the negatively charged proteins inside the neuron. The sodium-potassium pump moves sodium ions out of the neuron and potassium ions in. When the membrane is at rest, both the electrical gradient and the concentration gradient would act to move sodium ions into the cell, except that its gates are closed. The electrical gradient tends to move potassium ions into the cell, but the concentration gradient tends to move it out. The two forces almost balance out, but not quite, leaving a net tendency for potassium to exit the cell. The all or none law. For any stimulus greater than the threshold, the amplitude and velocity of the action potential are independent from the size of the stimulus that initiated it. When the membrane is sufficiently depolarized to reach the cell's threshold, sodium and potassium channels open. Sodium ions enter rapidly, reducing and reversing the charge across the membrane. This event is known as action potential. After the peak of action potential, the membrane returns towards its original level of polarization before the outflow of potassium ions. The action potential is regenerated at successive points along the axon as the sodium ions flow through the core of the axon and stimulate the next point along the axon to its threshold. The action potential maintains a constant magnitude as it passes along the axon. In axons that are covered with myelin, action potentials form only in the nodes that separate the myelinated segments. Transmission in myelinated axons is faster than in unmyelinated axons. Immediately after an action potential, the membrane enters a refractory period, during which it is resistant to starting another action potential. Local neurons are small, with no axon. They convey information over short distances. And contrary to popular belief, people use all their brain, not some smaller percentage. And that is the end of Chapter 1. Thank you for listening.